Okay, so first order kinetics. So first order kinetics, our rate law is going to have to be rate equals K times the concentration of some chemical to the first power. When I talk about first order kinetics, this is not first order for two chemicals, okay? It is first order overall, but the word overall isn't put up, okay? When you have first order kinetics, you get a natural log relationship to predict the concentration, okay? So, and that's where we're going both in this lesson, that's first order, and the second order, which is our next lesson. What is the concentration time relationship? We want to be able to make predictions. If we know we start at 1 mole per liter, how much do we have 3 minutes from now, 20 minutes from now, an hour from now? Okay. So the natural log of the concentration at some future time, okay, divided by the concentration of the reactant at the beginning. Okay. So we really have a natural log of a ratio. What is the ratio of how much we have to how much we started with? At the very beginning, this ratio will always be 1. Okay. If we start with 1 mole per liter, at the very beginning, we still have 1 mole per liter, would have 1 over 1. Okay. Over time, the numerator will decay, so our ratio will decay from 1 down to eventually 0 when we run out of A. The log of that ratio is minus KT, the rate constant times time. Okay. Okay. A common skill is to be able to take reactions and graph them and figure out constants or relationships graphically. So that's where we're heading next. We're going to rearrange this, and we can get a linear relationship when we rearrange it, turn it into y equals mx plus b. So the first thing I want to do to get a graphical version of this is split that reaction ratio apart. Okay? This is what I'm calling the reaction ratio. Okay? So we have the natural log of a fraction, so we can take the natural log of the numerator and subtract the natural log of the denominator. So that's the natural log of the numerator. I want to apply the natural log to the denominator. That'll show up as a subtraction. Okay. Now that black version is the version you typically see on your formula sheet, but I always start teaching this from the reaction ratio. So I'm just going to flip to a couple year ago formula sheet, and that's what's given, but you're not told that's the first order kinetics equation. You have to realize that. I'm just going to move this piece over. That is going to be a constant. That's just minus the natural log of whatever we started with. That will not change during the experiment. So the natural log of the concentration with respect to time equals minus KT. Now the minus natural log of the initial concentration will become plus natural log of reactant A initially. And now we have a linear version. We can plot time. That is going to be our x. Our k value will be our slope, or minus k value will be our slope. So it's a way we can get the rate constant. This is going to be our b value. And the y that we need to graph isn't the concentration in the future. We have to plot the natural log of concentration to get a linear relationship. Okay. So that's what we have down below. Let's fill in the correct variables. So we can plot time, okay, typically in seconds on the x-axis. The y needs to be the natural log of concentration over time. Okay. The initial value will be our b, so we're going to start at the natural log of concentration at the very beginning. And our slope is minus k. So on a test, I'm probably not going to ask you to take data and graph it. That might be a lab skill. That'd be time consuming. But if you're given a graph on the exam, you can determine the k value from the graph. Okay? You should be able to do rise over run fairly quickly and get the slope. Okay. If you do plot just straight up concentration versus time, so you don't take the natural log of it, you get an exponential decay. So you're going to start at the initial concentration, which would just be our A0, and it's going to drop faster at the beginning because you have the highest concentration, and then the rate is going to slow down as we start running out of A, and eventually it'll go to no A, eventually it'll go to 0. Okay. Now, this isn't that useful. This is the version, the linearized version that lets us get the k value. There's no nice way to get the rate constant if you don't plot the natural log version, so that's why we want to do it. Next, once we sort of have a little appreciation for the relationship, we can turn it into a linear relationship. I want to talk about that reaction ratio at the top. It's why I like this version, not the AP formula sheet, to see this. And then we're going to talk about half-lives a couple slides from now. Okay. So the reaction ratio, I'll repeat that top formula. That's what I'm referring to as the reactant ratio. We're going to look at that ratio versus percent of reaction. I just wrote percent in my little table, not percent of reaction. And I already mentioned at the very beginning, when you haven't used up any A chemical yet, this ratio is 1. If you started at 0.25 moles per liter, you still have 0.2 moles per liter. You have 0% reaction. When you have used up 10% of the reactant, you're 10% forward. Okay. So if we think of what's going on, the ratio would originally be, let's say, 1/1 if you had 1 mole per liter. 10% in, you've used up 10% of 1. So the top would now be down to 0.9 after you've used up 10% of it. Okay. And you'd always get that ratio. When you've used up 10% of the top, you're always going to get 0.9 as a reaction ratio. So the percent of reaction and the ratio kind of work opposites to each other. As the percent goes up from 0, the ratio drops down from 1. So if you went to 50% into the reaction, you've now used half the top. Okay. So you're going to get a reaction ratio of 0.5. When you're 75% into the reaction, okay, you're gone well past half. There's now only 0.25 left on the top compared to 1 using my 1/1 original starting point. So this isn't going to be continuous. So I'm just going to put a line. I'm kind of ending that trend. Let's say you had a reaction ratio of 0.42. So the bigger that ratio is, the closer you are to the beginning. So we went from 1 all the way down to 0.5, and then a little bit further past the halfway mark. Or if we just think of 1 minus 0.42, that'd be 0.58. So we're 58% into the reaction. Okay. I just put a line here. The blue is a trend, and then this is just an example of flipping between the two. It's not, that's why I switched colors and put a line. Okay, so, and this leads to one very common reaction ratio is 0.5 when you're halfway. That's referred to half-life, when you've used up half of a reactant. So half-life is the time to consume %50 of a reactant. So if we want to solve for half-life, we're going to have the natural log. The reaction ratio to use up half the chemical is going to be 0.5 equals minus K, and then I'm going to call this T1/2, not just T. So the natural log of 0.5 divided by minus K is T1/2. The natural log of 0.5, and the minus is values you can just all combine. And this is the version that you often have on a formula sheet. This is the half-life relationship, but only for first order kinetics. It's not true for 0 or second order. So I'm just going to flip this is the 2020 version of the AP formula sheet, and there's that T1/2 reaction, but it's not labeled that this is first order, and this isn't labeled that that's just first order. So you don't have to memorize the formulas, but you do have to know when they're applicable. They're not always applicable to all relationships. So we're going to talk about half-lives graphically next. So we get this type of graph when we look at first order kinetics. This is not the natural log version versus time. This is time in seconds plotted against the concentration versus time. So that's an exponential decay. But we have some consistencies in the decay. The half-life for first order kinetics is always the same length. It doesn't change with multiple halvings. So if you start at 0.2 like we do graphically, to cut in half would be 0.2 down to 0.1. And even without that red line put in, you should be able to realize, okay, 0.2 to 0.1 is half as much. You can go over and down and read off your graph what the half-life is. And it comes out as 7 seconds is the time it took to drop from 0.2 to 0.1. And that 7 seconds is going to be consistent for follow-up halves. So if you go from 0.1 to half of that, 0.05, that's another cut in half. And if you look at the time it takes to go drop from 0.1 to 0.05, that's going to be another 7 seconds, and it's always a consistent time. We cut it in half again, 0.05 to 0.025. We have another 7 seconds. So there. So every 7 seconds, it's going to cut in half. So we can make predictions, or if we know that the chemical has gone from the beginning to 1/8, we can actually figure out how many halves that is and what the half-life would be. So let's say you're told the half-life is 10 seconds. We're going to look at the time versus how much has been used up. At 0 time, we've used up 0%, or we're going to do these as fractions. So if we go out 10 seconds, we're going to have used up half of whatever starting amount of chemical we had. If we double that to 20 seconds, that's a second half-life. So we're going to be down to a quarter of how much chemical is left. So 50%, a quarter, we've now used up 75%. We go another 30 seconds, we're down to 1/8. I'll just do one more. We go another 10 seconds, we're at 40 now. We've got a 16th left. Okay, so you can kind of do this backwards and figure out half-lives. Okay. So we're told we have a first order reaction, that's important. Second order kinetics, half-lives are not doubles. The half-life is a function of the original concentration in second order kinetics. Okay. So we have a first order reaction, and it takes 90 seconds to consume about 88%. Okay. And I'm asking, what is the half-life? So there's a fair number of ways you could tackle thinking about this. I'm going to do it sort of by brute force, but you can come up with shortcuts and other methods for doing this. So we kind of rebuild that table and think of, okay, how many half-lives do we have? So we have 87.5% consumed. So we have to think of what's left. Okay. After one half-life, there'd be 50% left. After two half-lives, 25%. We'll have to keep going. So this would actually be 12.5% left over. Okay. We got to figure out how many half-lives to get to 12.5. Okay. So one half-life will leave 50%. Two half-lives would be down to 25%. We're going to cut that 50 in half. Or I talked about fractions before. That'd be a half. That'd be a quarter. Okay. If we go another half-life, we're down to 12.5% left. That's an eighth. If we go another half-life, we're down to 7.25% left. That'd be a 16th. So how many are we? We went down, 87.5% was consumed, 12.5% was left. So that's 3 half-lives. So we're told that 90 seconds occurred, but there's 3 half-lives to get all the way down to 12.5%. So each half-life must take 30 seconds. So in 30 seconds, we're down to 50%. 60 seconds, we're down to 12.5% left. 90 seconds, we're down to that 12.25% left. Okay. So these are often questions. You don't need a mathematical formula. You just want to sort of think through and have an understanding of what half-life means, and you can figure out how many there are. Okay. If you only used up 25% of something and you knew that time, 25% would be only like halfway. Okay. If you knew it took, 12 seconds to do half a half-life, well, double that would be the full half-life. Okay, so you can do it even if you undershoot a half. We'll wrap things up just by doing a bunch of math and making sure you're comfortable with that natural log button that often isn't used a lot. Okay, so we're going to do some questions with this relationship. We could solve for K, we could solve for T, or we could solve for the concentration of A at some time. We're never going to solve for the initial amount. That's something you're always going to be given. So first of 3 final questions. Cyclopropane can be converted to propene at 500. The rate constant is 500. The rate constant at 500 degrees Celsius is 6.7 times 10 to the minus 4. And we're wondering what is the how long for the concentration to drop from 0.15 molality to 0.1 molality. Now we've finished organic chemistry, so just giving you a visual of that reaction in that top white space. So we have cyclopropane got heated. We just have one reactant, which is what's leading to the first order kinetics, and this is turning into propene. That is balanced. They are isomers of each other in this reaction. So we need our first order kinetics relationship, and we just want to solve for time. We know everything but T. So the natural log of concentration at the beginning versus the concentration over time versus the beginning is minus KT. So the natural log concentration has dropped to 0.100. Divide by the original. We kind of have a lot of freedom on units in the reaction ratio because they're going to cancel. So we just have one thing to move to solve for our time. So time is going to equal so I just want to plug all of this into my calculator in one step, and I get 550 seconds. Big M's cancel. We have inverse seconds on the bottom, so we just end up with seconds. We have 2 sig figs, so I've rounded to 2 sig figs. Now you might be asked to convert this to hours or minutes. If you divide this by 60, it's a little over 9 minutes. B, so second of 3 questions. How much cyclopropane is left after an hour? So our rate, our K value is in seconds, so we can't put hours in. So there's 60 minutes in a second, 60 minutes in an hour. So that is 3,600 seconds. A lot are probably very comfortable or used to that second to hour conversion. we have natural log of concentration at some time divided by the beginning. We're going to have to split this ratio up because we're solving for one of those two pieces. Equals minus KT. I'm going to split and fill in. So the natural log of concentration at some time, that's really what we're after, minus the natural log of the concentration at the beginning, 0.145. Okay. Now I'm going to start simplifying, and the new part is going to be getting rid of that natural log function. That's the big part of this example, seeing the math. So the natural log, I'm not going to isolate for just the concentration of A at some time yet. I want to get everything on the other side. So I have minus 2.412 plus what I've brought over. So the natural log of what we want to solve for equals minus 4.343 when I put the two terms together. And now what is probably new math, to get rid of a log base 10, you'd make each of these numbers the exponent of a base 10 log, but this is a natural log base e. So to solve this, I'm going to go e to the natural log of the concentration equals e, the natural number, Euler's number. So e to the natural log, those cancel each other out. So I kind of dropped my unit analysis through this to just focus on the algebra, okay? But the concentration has to be in moles per liter. It's coming from the units have to cancel in our reaction ratio. So both of these have to be in molality. Okay. So we got our concentration after an hour. It's dropped a significant amount. Last question, and then we're done our first order kinetics lesson. Playing with reaction ratios. How long till 90% of the cyclopropane is turned into propene? This question is requiring us to figure out what that reaction ratio is. So how long till 90% is converted? So 90% has been used up. 90% of the numerator is gone. Okay, there's only 10% left. Okay, now we don't know what the bottom is, but anytime there's 10% of the top compared to the bottom, you're going to get 0.1 as a ratio when 10% of the numerator is gone. So we have the natural log of 0.1. Okay. And we can rearrange and solve for time. And to two significant figures, I got 3,400 seconds. So I know 3,600 is an hour, so it's a little bit under an hour. It's 200 seconds shy of an hour to get down to 90% left. Okay. So that's our first order kinetics. A lot of questions are first order. We've got second order to do. I'll tie zero order in really quickly in the next lesson, but there's not much to do with zero order type questions. Okay. So for practice in the Edvantage book, number 48, 1 and 2, page 55, the answer is right below sample problem 1.5.4. But I think it's good to work through that problem, and then right below you've got the answer. You can just put a piece of paper over it, and then on page 56, number 1 and 2 is my selected practice. Once we finish second order kinetics, we can work through the end of chapter questions at the end of 1.5, and then you'll be having first and second order kinetics all mixed together. And that's good to practice before a unit test or the advanced placement exam, having them humble jumbled and knowing which equation to use.